Good morning, students. Good morning, math enthusiasts. Today we are going to discuss about proving geometrical statements using concepts in circles part 2. So this video is a continuation of the previous video on the same concepts in circles. So again, the principles used here as well as the examples were taken from Chom's outline in geometry, but the illustrations and the flow of the proof were made by yours truly. Let's have the definitions of tangents related to tangents. The length of a tangent from a point to a circle is the length of the segment of the tangent from the given point to the point of tangency. So we have here the length, the point of tangency at A, and to this particular point, then that's the length of a tangent. We have here some principles on tangents. So principle 1. A tangent is perpendicular to the radius drawn to the point of contact. So a tangent, we have here tangent PQ, or we can name it tangent PA, which is perpendicular to this particular radius. Principle 2, a line is tangent to a circle if it is perpendicular to a radius at its outer end. So if this line is perpendicular to this radius at its outer end at this particular point of contact, then this line is a tangent. A line passes through the center of a circle if it is perpendicular to a tangent at its point of contact. So if this line is perpendicular to this tangent, then this line is a radius, and if we continuously move on, then we have a diameter. So this line passes through the center of the circle. Principle 4, tangents to a circle from an outside point are congruent. So notice that PB is a tangent, PA is also a tangent, and so these tangents, PA and PB, line segments PA and PB, are congruent. Principle 5, the segment from the center of a circle to an outside point bisects the angle between the tangents from the point to the circle. So as you can see, these are the tangents, line segment PA and line segment PB. Then this point outside, we have here a segment, we call it PO, then it bisects the angle between the tangents, meaning angle APO and angle BPO are congruent. The line of centers of two circles is the line joining their centers. So as you can see, these are the line of centers because these are the centers of these two circles, so O and P. So we have line segment OP. Circles O and P are tangent externally at A. So notice here that these two circles are tangents externally at A because there's a common tangent, line AB or line segment AB, or line AB is a common internal tangent of these two circles. Circles O and P are tangent internally at A with this form. So notice that this is the center of the bigger circle and this is the center of the small circle. These are not concentric circles. Okay, so we have here line AB as their common external tangent. Circles O and P overlap, as you can see. Then there's a common chord, which is line segment AB. Circles O and P are entirely outside each other. So as you can see, their common internal tangents are this one and this one. Line segments AB and CD meet at P. So AD must be equal to BC and FG must be equal to JI. Prove that. So we have here the first example. Prove that tangents to a circle from an outside point are congruent. So the hypothesis is tangents to a circle from an outside point, and the conclusion is that these tangents are congruent. So from the hypothesis and conclusion, we have here the illustration. Tangents to a circle from an outside point. So we have a circle, and then from the outside point B, we have two tangents, line BA and BC. Actually, it's a ray. So, but we call it a line segment BE because we stopped until here. So, line segment BA and line segment BC are two tangents. Then, we should prove that these two tangents are congruent. Well, actually, this was already a principle that has been presented, but we would like to discuss how it is being proven. So, the restatement is that circle O and line segment AB is tangent to tangent to circle O at A, and line segment BC or CB is tangent to the circle at C. Now prove that line segment BA or AB is congruent to line segment CB. So let's now have the marking. It says that line segment AB is tangent at A and line segment CB is tangent at C. Then we have to prove that these segments are congruent. So before that, let's draw two radii here connecting, which are perpendicular to our tangents, and as well as this line which divides these two angles, as we already know, into two equal parts. Okay, so of course all radii in a circle are congruent. So our goal here is to make these two congruent. So as you can see, there are two triangles. Then we can probably use the concepts on triangle congruence. So we start with this radii. Then also with this common segment. So we have two parts already. So what could be the third corresponding parts? So these angles. Because I have said that these are perpendicular to the tangent, so these two angles are right angles, and that these two triangles are right triangles, and so this is the hypotenuse, the common hypotenuse of the two triangles, and this leg, corresponding leg, so we can use the HL theorem for the triangle congruence. So after proving that these two are congruent, then by CPCTC, these sides here, the tangents are congruent. So let's start with our formal proof. So line segment AB is tangent at A, which was given. Line segment CB is tangent at C, which was given. So line segment OA and line segment OC are radii of circle O, and line segment OB is a line connecting the exterior point B and the center of the circle. So these are by construction. So line segment OA and line segment OC are congruent because all radii in a circle are congruent, and that line segment OA is perpendicular to line segment OB, as well as line segment OC is perpendicular to line segment BC or CB, because a tangent is perpendicular to the radius drawn to the point of contact. And so angles BAO and BCO are right angles because perpendicular lines form right angles. And by definition of a right triangle, triangle BAO and triangle BCO are right triangles. And by reflexive property, line segment OB is congruent to itself. Line segment OB is congruent to line segment OB because of reflexive property, and that we have already three corresponding parts. But of course, because these two triangles are congruent, so that's the first corresponding part. So we have here two right triangles, so we only need two corresponding parts, but actually there are three because of the concept of the right angles. So triangle BEO and triangle BCO are congruent by the hypotenuse leg theorem. And finally, our conclusion, line segment AB is congruent to line segment CB by CPCTC or CSCTC. QED. Okay, so let's have now more concepts and circles on measurement of angles and arcs in a circle. A central angle has the same number of degrees as the arc it intercepts. A central angle is measured by its intercepted arc. So as you can see, the central angle here is actually equal to its intercepted arc. But do not say that the central angle equals its intercepted arc. An angle cannot equal an arc because they have the different notations, or we have different characteristics. It's AB, it's an arc, but this one is an angle. So they just have the same measures. So an inscribed angle is an angle whose vertex is on the circle and whose sides are chords. So an angle, or another way around, an angle inscribed in an arc has its vertex on the arc and its sides passing through the ends of the arc. Okay, so this is an example of an inscribed angle. Notice that its vertex is located on the circumference of the circle and not on the center. So if an angle is, the vertex of an angle is at the origin, or at the center of the circle, then it's a central angle. But if its vertex is located on the circumference, then it's called an inscribed angle. Let's have the principles on angle measurement. So principle number 1, a central angle is measured by its intercepted arc. So whatever the measure of its arc, it's also the measure of its central angle, of the central angle. Principle 2, an inscribed angle is measured by 1/2 its intercepted arc. So if this is the arc AC, and there's a particular measurement there, then the measure of this inscribed angle is just 1/2 of the measure of its intercepted arc. So principle number 3, in the same or congruent circles, congruent inscribed angles have congruent intercepted arcs. So as you can see in the circle, if these angles, these are inscribed angles and happens to be congruent angles, then its intercepted arcs, arc AC and arc FD, must also be congruent. And also, if we have another circle and it happens that this inscribed angle is equal to the measure of this inscribed angle, then arc AC is congruent to arc GI. Principle number 4, in the same or congruent circles, inscribed angles having congruent intercepted arcs are congruent. So this is the converse of the previous principle, so that if these arcs are congruent, then these inscribed angles are congruent. So if these arcs are congruent, then these inscribed angles are congruent. This is the principle 3. Principle 5, angles inscribed on the same or congruent arcs are congruent. So as you can see, if these are the inscribed angles, angle ABC and angle CDA, and notice that they intercept the same arc, diba? Or congruent arcs, of course, by itself, or the same arc, then these measures should be the same. So meaning these inscribed angles must be congruent. So for example, we have here another inscribed angle, and also with this one, they intercept the same arc, then they must be congruent. An angle inscribed in a semicircle is a right angle. So as you can see, this one is a semicircle, and then we have here an inscribed angle. Then this angle measure here must be a right angle. Principle 7, opposite angles of an inscribed quadrilateral are supplementary. So if we have here an inscribed polygon, which is an inscribed quadrilateral, then the opposite angles here are supplementary, meaning their sum is equal to 180 degrees, and also with the other pair. Principle 8, parallel lines intercept congruent arcs on a circle. So as you can see, suppose these are parallel lines, all of these lines are parallel or line segments, then these arcs must be congruent. So arc CA is congruent to arc DB, but not congruent to arc EC. It depends. So arc EC is congruent to arc FD, and arc GE is congruent to arc GF. Principle number 9, an angle formed by a tangent and a chord is measured by 1/2 its intercepted arc. So as you can see, we have here a tangent and a secant. So the angle formed, angle CAB, is just 1/2 of arc AB. So the measure of this angle is 1/2 the measure of this arc. Principle number 10, an angle formed by two intersecting chords is measured by 1/2 the sum of the intercepted arcs. So notice that these are two chords that are not diameters because they do not pass through the center. So if we want to look for the angle measure of angle CEA or angle BED. Okay, remember your vertical angles. Angles 1 and 2 are congruent by vertical angle theorem, but for any of these angles to be determined, we simply get 1/2 of the sum of its intercepted arcs, meaning arc AC plus the measure of arc BD divided by 2, and that's the measure of any of these two angles. Principle number 11. An angle formed by two seconds intersecting outside a circle is measured by 1/2 the difference of the intercepted arcs. So as you can see, these are secant lines from an outside point C. So the measure of angle C, if we want to know the measure of angle C or angle ACE or angle BCD, then it's equal to 1/2 the difference of the measure of arc AE and arc BD. So meaning measure of arc AE minus the measure of arc BD equals, and divided by 2, that's the measure of angle C. Principle 12. An angle formed by a tangent and a secant intersecting outside a circle is measured by 1/2 the difference of the intercepted arcs. So as you can see, we have here a tangent and a secant. So how do you get the measure of this? Also the same. Get the measure of arc AD minus the measure of arc AC. Then the difference is divided by 2 to determine your measure of angle B. Principle 13. An angle formed by two tangents intersecting outside the circle is measured by 1/2 the difference of the intercepted arcs. So as you can see here, we have two tangents. So how do we get the measure of angle B? It's simply getting the difference of the measure of arc ABC minus the measure of arc AC divided by 2. So we have here the summary of the principles that we had. So a table of angle measurement principles. The position in the vertex it's in the center of the circle. So it's a center angle. And that angle AOB is equal to arc AB. And it's by the concept of method of measurement by the intercepted arc. Now we have on the circle also is an inscribed angle. And the formula is the measure of angle ABC is equal to 1/2 of the measure of arc AC. So that's the method of measurement by 1/2 of the intercepted arc. On the circle also is an angle formed by a tangent and a chord. So this one. So the measure of this angle CAB is 1/2 the measure of its arc. So that's a formula by 1/2 of the intercepted arc. Then inside the circle is another, we have here the angles formed by two intersecting chords. So measure of angle 1, which is equal to the measure of angle 2, is just 1/2 of the sum of arc AC and BD. So by 1/2 of the sum of the intercepted arc. Then we have outside the circle by the 2 seconds. So it's angle C is just 1/2 of the measure of arc AE minus arc BD by 1/2 of the difference of the intercepted arcs. Also, we have outside the circle the angle formed by a secant and a tangent. Angle B, the measure of angle B is 1/2 of arc AD minus arc AC by 1/2 of the difference of the intercepted arcs. Outside the circle again, we have angle formed by two tangents. Measure of angle B is just 1/2 of measure of ADC, arc ADC minus arc AC by 1/2 of the difference of the intercepted arcs. So let's have another problem. Suppose that you are given that the measure of arc BD and arc ECE are equal, then you have to prove that AB and AC are equal. So let's have the marking. Arc BD is congruent to arc EC. So what's going to be next in order to prove that these are congruent? Okay, so we have to prove that these are congruent. And so that is done if these angles here, the base angles, are congruent. So remember your your isosceles triangle theorem and the converse of the isosceles triangle theorem. So for this to be congruent, we should prove that these angles are congruent. So how is it done? So as you can see, these angles are actually intercepting this arc and this arc. So there's a common arc. So by reflexive property, it's congruent to itself. And so by adding this arc and this arc, then that will be related to the measure of this angle. Notice that these arcs are congruent, so what can you say about the sums? Also congruent. So that means these angles are congruent, and so these sides must be congruent. So we have the formal proof. The measure of BD, arc BD and arc ECE are given to be equal, and the measure of arc DE is congruent, equal to the measure of arc DE by reflexive property. Measure of arc BDE is equal to the measure of arc CED, because if equals are added to equals, their sums are equal. And the measure of angle B is congruent or equal to the measure of angle C, because inscribed angles having congruent intercepted arcs are congruent. And finally, AB is equal to BC or AC because of the converse of the isosceles triangle theorem, QED. Another problem, prove that parallel chords drawn at the ends of the diameter are equal in length. So the hypothesis is the parallel chords drawn at the ends of the diameter, and the conclusion is that these chords are equal in length. Alright, so here is the illustration. Parallel chords are drawn at the ends of the diameter. So these are the parallel chords, and this is the diameter. So we have to prove that these chords are equal. So the restatement is, given the circle O, line segment AB is a diameter, and that line, the chords AC, line segment AC is parallel to line segment BD. Prove that AC is equal to BD. So let's go to the marking. So since we were given that AB is a diameter, so it's here, as well as these lines to be parallel, then we have this notation. Okay, so we have to prove that these two lines are equal. And this could be done by considering these inscribed angles. Okay, notice that these are inscribed angles but are congruent because of the PAI theorem. Remember the PAI theorem? Ningon si PAI theorem that the alternate interior angles are congruent. But actually, you can directly say that these arcs are congruent because of the parallel lines. But if you wanted to go back with the previous discussion, so automatically by the PAI theorem, you can say that these are congruent. Or if you consider only the principles on circles, you can directly say that arc AD is congruent to arc CB because these are parallel chords. So that's it. And so, if these are congruent arcs, and of course this is a semicircle, so you can see that the remaining here are also equal by subtraction property. So let's have the formal proof. Line segment AB is a diameter which was given, and the measure of arc ACB and arc BDA are equal because a diameter cuts a circle into two equal semicircles. And so line segment AC and BD are parallel, which was given, and that angle CAB is congruent to angle DBA by the PAI theorem. But actually, you don't have to go through this item. I just included that only for the benefit of recalling your pi theorem. But you can directly state that the measure of arc AD is equal to the measure of arc CB because congruent inscribed angles have congruent intercepted arcs. And also, it's because these are parallel chords, and so this must be congruent arcs. And so arc AC and arc BD have equal measures because if equals are subtracted from equals, their differences are equal. So that line AC is equal to line BD because equal arcs have chords that are equal in length. So that is all for today. So we are done with all the concepts in circles, and we have I have shown to you three examples on proving geometrical statements containing concepts of circles. So remember, math is easy to learn when one learns with enthusiasm. Bye!